Let's look at some properties of continuous functions. Okay, a function f of x is said to be bounded above in the set D, domain of the function, a proper subset of real numbers. If two conditions are satisfied, f of x is defined in the set B, and second is that there exists a value m, let's say, belonging to the real number, such that the function is always less than or equal to this number for all x belonging to D, then f of x is said to be bounded below in the set D, a proper subset of real numbers. If, again, two conditions, f of x is defined in D, and the second is there exists m belonging to the set of real numbers such that f of x is always greater than or equal to m for all x belonging to D. Now here, bounded above, let's make this as capital letter M. Yes, just so that we can, by looking at this itself, we know it is a bigger one. Okay. Now, naturally, if we combine the above two, we can say f of x is said to be bounded in the set D, a proper subset of real numbers, if these two conditions is satisfied. F of x is defined in the set D, and second is there exists two numbers, that is capital M and M, both belonging to the set of real numbers, such that f of x is always less than or equal to capital M and f of x is always greater than or equal to M for all x belonging to D. So graphically, if you think about it, let's say we have something like this. If we have the curve going beyond this, but here it stops at this point, then we say it is bounded above. Whereas if it goes like this but it stops here, then we say it is bounded below. Whereas if we have a curve like this, it stops here and it stops here, then we say the curve is, or the function is, bounded. So let's look at some examples. F of x is equal to cos x is bounded function. Why? Because f of x is always, since cos x is always between 1 and minus 1, or rather minus 1 and 1 for all x belonging to the real numbers. Similarly, if you look at f of x is equal to 3x square plus 2x plus 3, and if we have put a restriction on the values of x, so we can say f of x is bounded in a comma b, where a and b belong to the set of real numbers. Okay, f of x equal to log x for 0 to infinity. Now here f of x is not bounded. F of x equal to 1 by x is bounded in 1 comma 2 and is not bounded in 0 comma 1. And here x again belongs to the set of real numbers in both the cases. Now the best way to look at this is understand this is look at the graphs of the functions. Use any graphing calculator and look at the graph between 0 and 1 and 1 and 2. Okay, so now let's look at the next property. A real number is said to be the least upper bound or supremum of the function f of x defined for a comma b. If m is a upper bound of f of x in a comma b, and second is for all epsilon greater than 0 there exists at least one point x1 belonging to this interval AB such that f of x1 is greater than m minus epsilon. What this basically means is that any real number smaller than m cannot be the upper bound of the function, and this is called the least upper bound, or in short LUB. Then a real number, here I should have mentioned a real number m. Yes, I didn't mention it. Okay, and that is the m we are referring to here. A real number m is said to be the greatest lower bound or infimum of the function f of x defined over the interval a comma b. If m is a lower bound, it has to be a lower bound of f of x in the interval AB, and for all epsilon greater than 0 there exists at least one point such that f of x is less than m, not capital, here I kept it as plus epsilon. Again, what this means is that any real number greater than m cannot be a lower bound. That is why this is called the greatest lower bound, or in short GLB. So we have looked at what all? We have seen that a function is bounded above based on these conditions. It is bounded below. It is called bounded if it is bounded both above and below. And then we have something called as least upper bound, and we have greatest lower bound. Understand this, because this is going to be very important as we go ahead. That's it for now. Bye.